Welcome to this GCSE revision video on energy changes in chemistry. We will cover exothermic and endothermic reactions, energy transfers, reaction profiles, and bond energy calculations. We will break down this topic into 4 manageable sections. We'll start with energy changes and transfers, then define exothermic and endothermic reactions with examples, and finally look at reaction profiles and bond energies. Chemical reactions involve energy changes as bonds are broken and formed. Energy transfers either into or out of the reaction system. The key idea is that energy is conserved. It's only transferred, not created or destroyed. The reacting chemicals are the system, and everything else is the surroundings. Energy transfer causes a measurable temperature change in the surroundings. A temperature rise means energy transferred to surroundings. A fall means energy transferred from surroundings. Exothermic reactions transfer energy to the surroundings, causing the temperature to rise. Products have less chemical energy than reactants, so the overall energy change, delta H, is negative. Remember, exothermic means energy exits. Combustion is a common exothermic example. Burning fuel releases heat and light energy to the surroundings. Products like carbon dioxide and water have less chemical energy than the reactants, which is felt as the flame's warmth. Neutralization is another exothermic reaction. When an acid and an alkali react, energy is released to the surroundings. This causes the reaction mixture's temperature to rise, which is often a required practical in GCSE Chemistry. Cellular respiration is a biological exothermic reaction. Living organisms break down glucose to release energy, which powers bodily processes and maintains body temperature. This is a key example to know for exams. Other everyday exothermic reactions include hand warmers using iron oxidation, setting cement, and explosive reactions like fireworks. Electrochemical cells or batteries also rely on exothermic reactions. Endothermic reactions absorb energy from the surroundings, causing the temperature to decrease. Products have more chemical energy than reactants, so the energy change, delta H, is positive. Remember, endothermic means energy enters. Here's a quick summary comparing exothermic and endothermic reactions based on energy transfer, temperature change, product energy level, delta H value, and common examples. Photosynthesis is a crucial endothermic example. Plants use light energy, absorbing it, to convert carbon dioxide and water into glucose and oxygen. This stored chemical energy is then fundamental to life on Earth. Thermal decomposition is another endothermic process, requiring a continuous input of heat energy to break down a compound. For instance, heating calcium carbonate to produce calcium oxide and carbon dioxide stops when the heating stops. Cold packs are a practical endothermic application. When the salt dissolves, it absorbs heat energy from the surroundings, including the skin, causing the area to cool. This decreases swelling and relieves pain after an injury. Other endothermic reactions include cooking an egg, which requires continuous heat input to denature proteins. Electrolysis also requires electrical energy input to decompose water into hydrogen and oxygen gas. Activation energy, EU, is the minimum energy needed to start any chemical reaction. This energy is required to break the existing bonds in the reactant particles. Catalysts accelerate reactions by lowering this activation energy barrier. Lighting a match demonstrates activation energy. You must strike it to provide the initial energy needed to break bonds. Once started, the exothermic combustion releases enough energy to sustain the reaction without further input. A reaction profile diagram plots energy against the progress of the reaction. The x-axis shows progress, and the y-axis shows chemical energy. The peak represents the transition state, and the difference between the reactant's energy and the peak is the activation energy, EUOD. In an exothermic profile, products are at a lower energy level than reactants, meaning energy is released, and delta H is negative. The hump shows the activation energy that must be overcome first. In an endothermic profile, products are at a higher energy level than reactants, meaning energy is absorbed, and delta H is positive. Activation energy is still needed, but the final product energy is higher than the starting reactants. This table summarizes the differences. Note that products are lower in exothermic reactions and higher in endothermic ones. A catalyst only lowers the activation energy hump. It does not change the energy levels of the reactants or products. To break a chemical bond, energy must be supplied from the surroundings, making bond breaking an endothermic process. The stronger the bond, the more energy is required. Remember, breaking bonds always requires energy. Conversely, when new bonds are formed, energy is released to the surroundings. This is an exothermic process. Every reaction involves both bond breaking, energy in, and bond making, energy out. The overall energy change, delta H, depends on the energy balance. If bond making releases more energy than bond breaking absorbs, the reaction is exothermic. If bond breaking absorbs more energy, it is endothermic. To calculate the overall energy change, first, sum the energy required for bond breaking in the reactants, which is energy in. Second, sum the energy released during bond making in the products, which is energy out. Finally, calculate delta H as energy in minus energy out. For the reaction H2 plus Cl2 forming 2HCl, bond breaking requires 679 kilojoules per mole. Bond making releases 864 kilojoules per mole. Delta H is 679 minus 864, resulting in a negative 185 kilojoules per mole. This negative value confirms the reaction is exothermic. The law of conservation of energy dictates that energy is only transferred, never created or destroyed. In a chemical reaction, any energy lost by the chemicals is gained by the surroundings, and vice versa. Delta H measures this net transfer. Exothermic reactions are vital for heating, transport, and practical applications like hand warmers. Examples include burning gas in boilers, combustion in petrol engines, and the oxidation used in hand warmers. Endothermic reactions are used where cooling or energy storage is needed, such as instant cold packs and refrigeration. Photosynthesis is a key example, storing light energy in chemical bonds. Industrial furnaces also rely on endothermic thermal decomposition. In exam questions, interpret reaction profiles by comparing product and reactant energy levels to determine if it's exothermic or endothermic. Accurately label the activation energy, delta H, and show how a catalyst lowers the activation energy hump. A catalyst provides an alternative reaction pathway with a lower activation energy, appearing as a shorter hump on the profile diagram. Crucially, the energy levels of the reactants and products remain unchanged. Only the activation barrier is affected. Typical exam questions test your understanding of reaction profiles. Be ready to classify reactions as exothermic or endothermic, label activation energy, and describe the effect of a catalyst on the profile. For bond energy calculations, remember to total the energy required for bond breaking, then the energy released during bond making. Calculate delta H as energy in minus energy out. A negative delta H, like the minus 93 kilojoule per mole here, indicates an exothermic reaction. In the required practical to measure energy changes, use a polystyrene cup calorimeter to minimize heat loss. Follow the steps. Measure volumes at initial temperature, mix reactants, record the maximum or minimum temperature, and calculate the temperature change. Common errors in the practical include heat loss and inaccurate temperature readings. Improve accuracy by using a polystyrene cup with a lid, a digital thermometer, and repeating the experiment to calculate a mean temperature change. Review these key definitions. Exothermic reactions transfer energy to the surroundings, while endothermic reactions absorb energy. Activation energy is the minimum energy required to start a reaction, and the reaction profile charts energy against reaction progress. More definitions. Bond energy is the energy required to break 1 mole of a bond. Delta H, the enthalpy change, is negative for exothermic and positive for endothermic reactions. A catalyst speeds up a reaction by lowering activation energy. Top exam tips. Always state the direction of energy transfer. Use the correct sign for delta H, show all working in bond energy calculations, and clearly label reaction profile diagrams with both activation energy and delta H. Avoid common misconceptions. Bond breaking requires energy, while bond making releases it. Exothermic reactions heat the surroundings. Catalysts only lower activation energy, and endothermic reactions still involve energy release, just less than absorbed. That summarizes energy changes in chemistry, covering the essential concepts for your GCSE exams. Good luck with your revision.